Welcome students to the first lecture of infinite series. In this and subsequent few lectures, I will be talking about series with infinite number of terms. This is a very important concept in analysis, as you will find that we can compute values for many functions for a given specific value of x. Say for example, sin x, cos x. For arbitrary value of x, we can compute using corresponding infinite series. Say for example, sin x, we have so far seen only for a few values, right. Say for 0, pi by 3, pi by 4, pi by 6 or pi by 2, something like that. But actually sine is a continuous function, and if you have seen the sine curve, it is defined for all the different values of x on the real line. Question comes, how do you compute the value of sin x for any arbitrary given value of x? So, this is true not only for sin x, many such functions are there, and therefore, infinite series gives us the way to compute such values. The basics of infinite series for computing functional values comes from YStress approximation theorem. Which suggests that if f is a continuous real valued function, defined on the closed interval then for every real x belonging to the interval a to b, and given any epsilon greater than 0, there exists a polynomial p such that for all x belonging to a comma b, modulus of f x minus p x is less than epsilon. So, this is very important. So, f is a continuous function in a b. Suppose this is the real line and this is a and this is b, and f is arbitrary continuous function, then at any particular value x, I can approximate f x with a polynomial. And you all know that polynomial of degree n is of the form, say a 0 plus a 1 x plus a n x to the power n. So, depending upon the value of epsilon, we can choose a large n, so that value of the polynomial will be close enough of the functional value f x. In other words, we can approximate f x by a polynomial p x. So, if for an arbitrary function say sin x, if we can find a polynomial function to approximate sin x, then we are done. The question is how to obtain such a polynomial. In order to do that, we have to look at a series Now, what is a series? In the IIT PAL lectures, we have dealt with sequence and series. You look at these lectures, you will get a foundation of sequence and series, but to explain the concept of infinite series, I will give you a small introduction to these two terms, sequence and series, and some examples, so that you can recapitulate those things easily. Okay? So, what is a sequence? A sequence is an ordered arrangements of certain entities or objects. For example, alphabet. If we consider English alphabet, we have A, B, C up to Z. These 26 letters come in that specific order, right? Nobody says C, Z, B, M. No, there is an order and that is the sequence in which the different letters occur in the English alphabet. Similarly, say rainbow colors. There is also a sequence violet, indigo, blue, green, yellow, orange and red. Now, a sequence can be numeric also, say prime numbers. What are the prime numbers? 2, 3, 5, 7, 11, 13. So, there is a specific sequence in which the prime numbers are occurring. Even numbers. If you look at them, they are 2, 4, 6, 8, 10. Now, we can see that two things we have to observe. Firstly, sequence may be finite or infinite. Right? Alphabet, colors of rainbow, etc. are finite sequence. What does it mean? That is, the number of terms is finite. Even numerically, we can think of, say, all odd numbers between 0 to 100. And we know there are only finite number of odd numbers, namely 1, 3, 5 up to 99. Finite sequences are somewhat easy to handle. We can easily find their maximum, minimum, sum, average, etc. But when it comes to infinite series, infinite sequence, that means the number of terms can be arbitrarily large. What does it mean? It means that you choose any large number n, the number of terms in the sequence is greater than n. That means, you can find more than n number of elements of that sequence. Example: all even numbers. All powers of 2. Say for example, 2, 4, 8, 16, 32. You can keep on increasing the values which are powers of 2. That is, given any k 2 to the power k belongs to the above sequence. The second issue is whether the sequence has a limit. Consider, for example, one, 2, 3 sequence of natural numbers. Does it have a limit? You all know that the answer is no. You can give me any number capital N, I will show that I can find an integer that is bigger than that. Similarly, two to the power k, k is equal to 1, 2, etc., does not have any limit. As you give me any big number n, I can always find a k such that 2 to the power k is bigger than that n. On the other hand, consider 1 plus 1 by k, k is equal to 1, 2, 3, etc. What will happen? At k is equal to 1, the value is the two. K is equal to 2, 1 plus half is equal to 1.5. At k is equal to 10, as you can understand, it is going to be 1.1. K is equal to 100, it is going to be 1.01. K is equal to 1000, 1.001. What do I find? That it will always be greater than 1 but as k increases it is close to 1, right. As k increases, the values are coming close and close to 1. A different type of example is the following. Consider minus 1 whole to the power n. If we write the sequence, it will look like the following: minus 1 power 1, next one is minus 1 power 2, next one is minus 1 power 3, next one is minus 1 power 4, and so on, and that is equal to minus 1 plus 1 minus 1 plus 1. So, we can see alternate occurrence of minus 1 and plus 1. So, as n increases, the values of the sequence are not converging to any value r, right. Therefore, this sequence also does not have any limit. Now, the next term that I like to explain is a series. You all know that given a sequence say A1, A2, A3 like that, where AK is the kth term of the sequence, the term, the summation A1 plus A2 plus A3 or sigma AI 1 to say sigma AK k is equal to 1, 2, 3, etc. is called the series corresponding to the given sequence A1, A2, A3, etc. Now, if the sequence is finite, and the terms are numeric, then we can easily obtain the value of the series or sum of the series. In fact, you have seen AP, GP, etc. And we have obtained the sum of the first n terms. Right? So, we know if a given series is in AP, then we know how to obtain the first n terms. If the given series is in GP or geometric progression, we know how to obtain the sum of first n terms. Question is, what happens if the sequence is infinite? That means, the number of terms in that sequence is infinite, e.g. a k is equal to 2 to the power k. Another example, a k is equal to 5 minus 2 k. Another example, a k is equal to sine of 2 k pi. Another example, a k is equal to sine of 1 upon 2 k pi by 2 or 1 upon k pi by 2. If you look at it, in each one of them there are infinitely many terms, right. You can always substitute the value of k in the formula for the corresponding sequence, and we can obtain the value of the kth term. So, if we add them, we get a series sigma k is equal to 1 to infinity a k. The question comes whether the series will converge to some particular value or not. That is, the question is, if the series is infinite, does it converge to some value, or does it have a limiting value? So, we do it in the following way. Let Sn be summation over a k for k is equal to 1 to n. So, this is called the nth partial sum. the nth partial sum. Okay? So, if we think carefully, we will understand that S 1 is equal to A 1, S 2 is equal to A 1 plus A 2, S 3 is equal to A 1 plus A 2 plus A 3, A n is equal to A 1 plus A 2 plus S n is equal to A 1 plus A 2 up to A n. Thus, actually we generate a sequence S 1, S 2, S n, and if this sequence has a limit, then the series A 1 plus A 2 plus A n as n goes to infinity will converge, or the series will converge if the corresponding sequence of partial sums S 1, S 2, S n has a limit. For example, let A k is equal to k. Then S n is equal to 1 plus 2 plus up to n, which is n into n plus 1 by 2, right. Therefore, as n goes to infinity, the nth partial sum S n also goes to infinity. Therefore, the series sigma k, k is equal to 1 to infinity, does not converge. Similarly, consider A k is equal to minus 1 to the power k. Therefore, A 1 is equal to minus 1, A 2 is equal to plus 1. We have already seen A 3 is equal to minus 1, A 4 is equal to plus 1, etc. And we can easily find that S 1 is equal to minus 1, S 2 is equal to 0, S 3 is equal to minus 1, S 4 is equal to 0, implies the series does not converge. Therefore, when discussing a series, we have to find out whether the series is convergent or not. If it does not converge, then we cannot get the value of the series, and therefore, if we want to use an polynomial of arbitrary degree to approximate a function f x, we will not be able to approximate that, as the series is going to be divergent. Now, let us consider geometric progression. All of you are aware that geometric progressions with first term A and the common ratio A r will look like this, right. That is, the kth term is equal to a r to the power k minus 1. We all know the partial sum, say s k. So, what is s k? S k is equal to a plus a r plus a r square plus a r to the power k minus 1. Therefore, r times s k is equal to a r plus a r square plus a r to the power k minus 1 plus a r to the power k. That is, s k minus r of s k is equal to a. Then as I am subtracting, they are all getting cancelled out, and what is left to it is a r to the power k is equal to a into 1 minus r to the power k. Therefore, we find that 1 minus r times s k is equal to a into 1 minus r to the power k. Therefore, s k is equal to a into 1 minus r to the power k divided by 1 minus r. So, we find that for the GP, s k is equal to a into 1 minus r to the power k upon 1 minus r, or we can write it as a into r to the power k minus 1 upon r minus 1, depending upon whether r is smaller than 1 or greater than 1, we get one of the expressions. What happens if k goes to infinity? That means we are looking at the geometric progression when the number of terms is infinite. Consider limit k goes to infinity a into 1 minus r to the power k upon 1 minus r. If modulus of r is less than 1, then we know r to the power k goes to 0. Therefore, this term as k goes to infinity goes to a upon 1 minus r as k goes to infinity. On the other hand, if modulus of r is greater than 1, then r to the power k goes to infinity. Therefore, limit k goes to infinity, a r to the power k minus 1 upon r minus 1 is infinity, and therefore, the series does not converge. Right? So, this is an important lesson for us. If we are talking about A, AR, AR square, or which is equivalent to A into 1 plus R plus R square, it will converge if modulus of R is less than 1, else it will diverge. This brings us to the interesting series 1 plus R square, like that. Where does it converge? If we look at the sum A into 1 minus R to the power k upon 1 minus R, that was the GP series we have got. Up to k terms. If modulus of R less than 1, this will sum up to A upon 1 minus R. In particular, keeping A is equal to 1, we can say 1 plus R square plus R cube, this series converges to 1 upon 1 minus R. For example, what is 1 plus half plus 1 by 4 plus 1 by 8 plus this sum? We know that there are infinitely many terms in the series. Therefore, as such we cannot compute the sum, but using this result we can say that this sum is 1 upon 1 minus half is equal to 2. Okay? So, we can compute this series using the concept of limit, that this series value is going to be 2. In a similar way, what is 1 plus 1 by 3 plus 1 by 9 plus 1 by 27, that is I am looking at 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 cube, that is I am looking at the series 1 upon 3 to the power k, k is equal to say 0 say infinity. This is going to be 1 upon 1 minus 1 by 3 is equal to 3. 3 by 2. So, this series will converge to the value 3 by 2, right. 1 minus r to the power minus 1 is equal to 1 plus r square plus this for modulus of r less than 1. Okay. Now, the question is, what about one plus r whole to the power minus 1? We can compute it easily from this. So, we are looking at one plus r whole to the power minus 1. We can write it as 1 minus r whole to the power minus 1. Therefore, putting the value of r is equal to minus r in the series expansion, we get 1 plus r whole to the power minus 1 is equal to 1 plus minus r plus minus r whole square plus minus r whole cube, like that. This is equal to 1 minus r plus r square minus r cube plus r to the power 4, like that it will go. Thus, if the value of modulus of r is less than 1, then in a similar way we can find 1 plus r whole to the power minus 1 as well. Have you seen similar expressions before? Yes, you did. Binomial expansion. If I asked you what is 1 plus r whole to the power n, you know the answer is 1 plus nc1 r plus nc2 r square up to ncn r to the power n, where nck is equal to factorial n factorial k factorial n minus k. Here n is this n a positive integer, right. So, we know how to expand one plus r whole to the power n for a given positive integer n. We also know that there are n plus 1 terms in the series. Since this is finite, we can compute today I have seen 1 plus r whole to the power minus 1. So, note that the power here is negative. Therefore, what has happened? We have seen for positive n finite sum or finite series, but for negative n we get an infinite series. In particular, we found that the series 1 minus r whole to the power minus 1 or 1 plus r whole to the power minus 1, we could compute their values. If modulus of r is less than 1. Now, I will stop here, but giving you some task. Try to do these. What is 1 minus r whole to the power minus 2 or 1 minus r whole to the power minus 3. Right? Okay, students. In the next class, I will start with these problems and I will show how we can obtain the values of such terms for a given value of r whose modulus is less than 1. Till then, you try to practice this. We will see you in the next class. Thank you so much.